Okay, welcome back to 11th grade chemistry. I offer all of my students universal support by printing out all of our handouts, all of our activities, but my student with me today, Katie, specifically has a visual impairment, so for any print handouts or copies of notes that I provide her, I make them in large print so that she can read them better. So today's lesson, we are going to continue talking about ionic compounds and ionic bonds, specifically making Lewis dot structures to represent how those electrons are used in an ionic compound. A Lewis structure is just a diagram we can use to model a bond. So before we get started, can someone just give me a quick reminder of what an ionic compound is? Yes, Kate.
A chemical compound composed of oppositely charged ions held together by ionic bonds.
Beautiful. So in an ionic compound, we are going to have two oppositely charged ions. And in each ionic compound, it's going to be composed of metals and non-metals. So, to create a Lewis structure, our first step is to write out the components of our compound. And the compound we're going to be looking at today is sodium chloride, simple table salt. And I've already written out our components. Sodium chloride is made up of sodium, which is Na, which I've written its chemical symbol down already, and chlorine, which is given the chemical symbol of Cl. Now first, we have to determine which of our atoms are our metals and which are our non-metals. Can someone tell me what groups on the periodic table the metals belong to? Katie?
1 through 12.
Yes, the metals fall in groups 1 through 12. Now what about our non-metals? Where can we find those? Katie?
14 through 18.
Yes, our non-metals fall in groups 14 through 18. So looking at our periodic table, what group can we find sodium in? Yes.
1.
Yes, it's in group 1, so that means it's going to be a metal. And now what about chlorine? Yes, Katie?
17.
Yes, chlorine's in group 17, so that means it's going to be our non-metal. So once we have decided which is our metal and which is our non-metal, we now have to fill in the valence electrons for each atom. So, knowing that sodium is a group 1 metal, how many valence electrons will sodium have? Yes.
1.
Yes, it'll have 1 valence electron. So, to denote that, I'm just going to make a dot above sodium showing that has 1 valence electron. Now, knowing chlorine is a group 17 element, how many valence electrons will it have? Yes.
7.
Yes, every element in group 17 will have 7 valence electrons. So I'm going to draw 7 X's around chlorine to show that. Now I'm drawing X's on chlorine and a dot on sodium just so we can identify the difference between the valence electrons from the two atoms. Now, in an ionic bond, our valence electrons to create the bond are transferred from the less electronegative atom to the more electronegative atom. Can someone just remind me what electronegativity means? Yes, Katie.
Tendency of an atom to attract electrons.
Yes, so a more electronegative element wants to pull in those electrons, which is perfect for an ionic bond because those electrons have to transfer over to the more electronegative atom. So, based off of our periodic trends that we learned about earlier, can someone tell me how electronegativity changes as we move from left to right across the periodic table? Yes, Katie.
It increases.
Yes, so as we move from group 1 to group 18 across the periodic table, electronegativity increases, which means that as you go from our group 1 sodium to our group 17 chlorine, sodium is going to be less electronegative compared to chlorine. So our lone valence electron on sodium is going to transfer over to chlorine. To show that, I'm just going to draw an arrow showing it's moving over to chlorine, and I'm going to draw that dot on chlorine, showing that that electron has moved over to chlorine now and is now a part of the chlorine. So our next step is to figure out the charges associated with each ion present in the chemical compound, because as we stated earlier, a chemical compound is composed of oppositely charged ions. So, how are we going to denote the charge now associated with sodium? Sodium has just lost 1 negatively charged electron to chlorine. So, how is its charge going to be affected now that it has lost 1 negative electron? Yes.
And it's going to become positive.
Yes, sodium is going to have a positive charge. So to do that, we're going to draw brackets around sodium and then draw a +1 in the top right corner to show that it now has a +1 charge. Sorry, I drew that a little small, but you get the point. Sodium now has a +1 charge because it has lost 1 electron. Now going over to chlorine, chlorine has just gained 1 negatively charged electron. So how is its charge going to change? Yes?
Negative.
Yes, chlorine is going to become negatively charged. So now I'm going to draw brackets around chlorine and write a -1 in the corner to show that chlorine now has that negative charge associated with it. So now we have formed our 2 ions that we need for our chemical or ionic compound. Now, really quickly, can someone tell me the special name given to the positively charged ion in an ionic compound? Yes.
A cation.
Yes, the positively charged ion in an ionic bond is called a cation. And then what's the special name we give to the negatively charged compound or atom in a chemical compound? Yes, Katie.
An anion.
Yes, the negatively charged atom is the anion. So, before we can say that we've fully completed our Lewis structure for this ionic bond, we need to make sure that our bond and our Lewis structure follow the octet rule. Can someone remind me what the octet rule is? Yes, Caitlin.
Atoms are most stable with 8 valence electrons.
Yes, so atoms like to achieve stability and they are most stable when they have 8 valence electrons. On the periodic table, we know that the only elements that are in their natural ground state with 8 valence electrons are the halogens, which is group 18. So since chlorine is in group 17 and sodium is in group 1, we know that they don't have a total of 8 valence electrons in their ground state. So they're going to chemically combine together to achieve getting those 8 valence electrons. So when we count up how many electrons we have, we know that our electron from sodium has transferred to chlorine, so we're going to focus in on chlorine, and we count up all of our valence electrons, and we see that we have 8, which is good. We have now met the octet rule, and we have completed making our Lewis structure. So now you guys are going to go off in your small groups and work on the Fruit Loops Lewis structure ionic bonding activity, and you're each going to be asked to present one of the examples from the sheet.
In this activity, to reinforce that electrons are transferred to the more electronegative atom in an ionic bond, students will create their Lewis structures using Fruit Loops to model this transfer of electrons. Students will be provided 2 elements that form an ionic bond, and they have to identify the metal and non-metal from each pair. After that, they will find the number of valence electrons present for each atom. Students will then place the correct number of Fruit Loops around each atom to represent their valence electrons, and then transfer the Fruit Loops from the less electronegative atom to the more electronegative atom. Students will be using 2 different colored Fruit Loops to distinguish between the metal and non-metal's valence electrons. Before they complete their Lewis structures, students will double check that their compound follows the octet rule. If it does not, then they will need to identify whether they need to add another metal or a non-metal to make sure the octet rule is followed. After that, they will then remove the Fruit Loops and draw in the electrons in their place. They will finish their structures by adding in brackets and identifying the associated charges of each atom, making sure that the sum of the charges on the atom matches the overall charge of the compound.
All right, so here we have Katie presenting number 10 from the worksheet. So Katie, can you tell me what elements you have from your compound that's the metal and which ones are the non-metal?
The potassium is the metal and the oxygen is the non-metal.
Beautiful! Now I noticed that you have 2 potassiums in your Lewis structure. How did you know that you had to put in 2 potassiums?
Since oxygen has 6 valence electrons, it's going to need 2 electrons transferred to it. Potassium is a group 1 element, so it only has 1 valence electron. So to get the 2 electrons, I added a second potassium.
I love it. That's such a great explanation. So during this activity, when you were working with your Fruit Loops, how did you show the transfer of electrons from the metal to the non-metal?
I moved the blue Fruit Loops from potassium to oxygen.
Great, because we said that our blue Fruit Loops are going to be the valence electrons associated with the metal. So you just moved them over. I love it. So how did you know that you had to move the Fruit Loops from the potassium to the oxygen?
The oxygen is more electronegative, so it has a higher attraction for electrons.
Good, so we know that oxygen is a group 16 non-metal, so it's going to be more electronegative compared to our group 1 metal potassium. So it's going to be more electronegative, draw those electrons to it, making our oxygen the anion and our potassiums the cation. Good, I love it. So how were you able to represent the resulting charges from on the individual ions in your Lewis structure?
I put brackets around the Lewis structure and wrote the charges as superscripts.
Beautiful, I love it. You got your charges in the top right corner. Beautiful. Now what's the overall charge of this compound?
0.
Yeah, it's 0 because we have 2 potassiums, each with a +1 charge, giving the potassiums an overall charge of +2, and our oxygen has a -2 charge, so when you add it together, you get 0. Beautiful, I love it. So what is the chemical formula for your compound?
K2O.
Good, and you have 2 potassium, so that's where you get the K2, and then 1 oxygen, so you just write, oh, beautiful. Now, what would you name this compound?
Potassium oxide.
Great, I love it. So that's all the time we have for in class today. We have just a couple minutes left, so make sure you go grab your exit ticket and hand those in on your way out.